So hello everyone, I am Shafiq. In this part of the presentation, we will explore the result presented in the DINOv2 paper. So the goal of the demonstration of the results is to show that DINOv2's self-supervised features outperforms the current state of the art in SSL and are competitive with or surpass the WSL features on many tasks. on many tasks. When coming to the baseline SSL and WSL models that are publicly available, so SSL models such as MAE, Dino, iBot are compared with the DINOv2, and WSL models such as Clip, OpenClip, EVA Clip, Swag are compared with DINOv2. Now, to assess the quality of the learned features, the authors used three evaluation methods: linear probing, few-shot learning, and fine-tuning. Now, these tests are run across the standard vision tasks such as classification, semantic segmentation, depth estimation, and image retrieval. So here is the results of linear evaluation on ImageNet 1K frozen pre-trained features. Here top one accuracy on the validation set for publicly available models trained on public or private data with or without text supervision are reported here. So in the top table you can see the weakly supervised models such as Clip, Swag, OpenClip, and EvaClip, and the architecture used are VITL, H, and G. So the data that have been used to train these models are also listed here, and you can see there are two strategies to evaluate the models. One, it was evaluated using KNN, and also it was evaluated using the linear classification. So here you can see the DINOv2 basically outperforms any of these methods such as self-supervised or weakly supervised previous methods. So you can see the previous version of Dino had accuracy of 79.2, and the current version or version 2 has accuracy of 86.5 on the VITG architecture. So it's quite an improvement over the previous generation of Dino or any generation of any version of SSL or WSL methods. Now these are some other results on image and video classification. So on image classification, OpenClip, MAE, Dino, and iBot are compared with this DINOv2 with different various VIT architectures, and for video classification, different datasets are used to compare the video classification results using the same linear evaluation method. And here you can see it has an accuracy of 78.4 on the K400 dataset and 91.2 on the UCF 101 dataset and 38.3 on SSV2 dataset, which doesn't outperforms the other SOTA models. The iBot actually has better performance than our DINOv2. Now the key takeaway is that DINOv2 has an accuracy of 82.8 using only linear probing method, that is without fine tuning, and this is better than previous SSL models such as Dino, iBot, and the MAE model. And the insight here we can take away is that DINOv2 produces highly linearly separable features, which is a hallmark of strong representation learning. Now coming to domain generalization results. Now coming to domain generation results, here also DINOv2 outperforms the SOTA models such as iBot, MAE and DINO. So it cannot outperform the OpenClip model, which has an accuracy of 87.8. So it has an IMR score of 87.8, IMC score of 28.2 and 75.9 of IMA score. And so for IMC, the lower the score, the better it is. So for IMC, it has a lower score, so it is performing better. And for the other two scores, IMA score has better than any other model, and it is has a score of 78.8 on IMR. Now the key takeaway from here is it generalizes very well, and it maintains a strong performance without any additional training. And unlike supervised models which may overfit to their level dataset, DINOv2 demonstrate robustness and transferability. So here are some more results on fine-grained feature. Here are some more results on uh, fine features on fine-grained benchmarks. So you can see various types of objects, scenes and textures are used to evaluate the model. So food, C10, C100, sun, cars, aircrafts, VOCs, pets, flowers, etc. They are used to evaluate the model generalization. So here you can see in most of the cases the model outperforms the SOTA models. So on image recognition or face recognition, it was tested on Oxford, Paris, Meta and Amsterdam datasets. So you can see here we have also it outperforms in most of the cases. Now coming to results dissection. So on the Oxford dataset, it has an score 75 MAP score and 54 MAPH score, and iBot has 40 and 13, and OpenClick has 51 and 20. Paris, on the Paris datasets, its score the scores are 93 and 84, and on the Met dataset it has an 69, and the gap is 69. So the takeaway is DINOv2's version features dominate both state-of-the-art self-supervised and text-guided models on all four instant retrieval benchmarks, proving they work equally well at instant and category granularity. Now coming to semantic segmentation, here you can see it was tested on various datasets such as AD20K, cityscapes and Pascal VOCs with frozen features, and in all of the cases, in most of the cases, it is outperforming the SOTA models. So the key takeaway is for semantic segmentation, DINOv2 features are plugged into mask to former and tested on AD20K, cityscapes and Pascal VOC, and it outperforms most prior self-supervised models. And the key insight is that it indicates that DINOv2 captures fine-grained spatial features critical for pixel level tasks. Now for depth estimation, it was tested on NYU depth V2, Kitty and Sun RGBD, Mostly DINOv2 performs subpar with task-specific models, and the key takeaway is its self-supervised features can encode 3D structure even without ever being explicitly trained on depth. And these are the results of the depth estimation with frozen features. So here you can see it is almost equally subpar with the SOTA models. Now coming to qualitative results, we can. So in this part, we'll explain the qualitative result. We will show the qualitative results reported in the paper, and this includes image retrievals, attention visualization, dense prediction, and which helps us understanding the DINOv2's perceives and processes how it processes images. Now here you can see the visualization of the segmentation and depth estimation of these models. So in the first image you can see one input was taken from the AD20K dataset, and how the results are compared with the OpenClip G with the DINOv2G. And you can see the DINOv2 always outperforms in all of the cases. So here you can see the over the depth estimation. Depth estimation is not good here. So the model is not performing well when estimating the depths of these objects in the images for the OpenClip, but the DINOv2 is performing well. And here also for segmentation, it has similar results, but it is with par with the SOTA models. So here you can see it segments the house very well. And here are some more results from the paper. So yeah, so these are the results from the OpenClip, and these are the results from DINOv2. Here visualization of the first PCA component. So you can see DINOv2 very well extract the PCA features, PCA components. So key takeaway is that for instant retrieval, DINOv2 really shines on datasets like Oxford 5K, Paris 6K, and MMet, and it achieves state-of-the-art retrieval accuracy, surpassing the clip and supervised VITs. And the key insight is that DINOv2 is particularly strong at learning global and local patch similarities, which is key for retrieval. Now the result section. So summary of the findings of the results are that DINOv2 achieves state-of-the-art performance in many tasks, such as many tasks often rivaling the supervised models, and it features a general, transferable, and robust, making it ideal for real-world applications and applications, so that careful data curation and training practices drive performance gains. Broader implication is that it shows it is now a practical alternative to supervised pre-training, especially in domains where labels are scarce, such as medical imaging, remote sensing, and robotics. And by releasing strong open source models, Meta AI has provided the community with a foundation that can reduce reliance on expensive supervised data.